This is a video for AQA Further Pure Mathematics, and this is Complex Numbers section 1.5, where we're considering the terminology connected with complex numbers. Well, we've talked about complex numbers usually given the letter Z to indicate a complex number being equal to A plus BI, where A and B are real numbers. The real part of the number, which is often written RE, capital R-E-Z, is equal to A, and A itself is a real number. B is what's called the imaginary part of the number, and that's written IM, capital IM for imaginary of Z. And that's equal to B, and B is also a real number. So notice both A and B are real numbers. Some confusion sometimes from students is that consider the imaginary part to be BI. It isn't, it's the real number B, which is the imaginary part of the complex number. We've also discussed in earlier videos the idea that if we take Z and its conjugate, which is called Z star, which is A minus BI, then if we form the product ZZ star, then we always get the real number, which is A squared plus B squared. If we have an equation which considers complex numbers on the left hand side and the right hand side, then for there to be an equality, the real part on the left hand side must be equal to the real part on the right hand side. Or in other words, in this particular case, we can say we're going to look at the real parts and say that A must be equal to 7. Likewise, the imaginary parts must be equal to each other on both sides of the equation. So here we have the imaginary part investigated, and therefore B must be negative 4. So for numbers to be equal to each other, both their real part and the imaginary part of the numbers must be the same. Now we can use this idea to do things such as division. So rather than looking at the idea of calculating the division of two numbers by using the complex conjugate, we could consider it in this way. We could say, well, for this equation 3 minus 2i over 5 plus I equal to A plus BI, we could multiply both sides of the equation by 5 plus I. And if we do that, obviously we get the following. Now, the right-hand side we can calculate in the usual way by looking at the first terms, the outside terms, the inside terms, and the last terms multiplied together. And if we do that, we'll get 5a from the first term, 5bi and ai, and then finally b multiplied by I squared. We can now consider that right hand side and decide exactly what we've got in terms of a real part and imaginary part. So remember that I squared is equal to negative 1, so that final part there is just minus b for that, so that the real part of this number is going to be 5a minus b, and the other part of the complex number, the imaginary, is going to be a plus 5b. So there we have 5a minus b for the real part and a plus 5b for the imaginary part. Now we can equate the left hand side to the right hand side looking at the real parts and the imaginary parts. So if we look at the real part first, on the left hand side we've got 3, and on the right hand side we've got 5a minus b. Therefore 3 must be 5a minus b. The imaginary part on the left hand side, negative 2, and on the right hand side a plus 5b. Now these are two pair of simultaneous equations which can be solved simultaneously, obviously. For example, if we took the first equation, the top one, and multiplied by 5, we would get 15 is equal to 25a minus 5b. And then if we consider adding that to the second equation, which is negative 2 equal to a plus 5b, you can see then that we would get 13 is equal to 26a, and therefore a is going to be a half, and if you then substitute, you'll find that b is negative half. So our number a plus bi, which is the result of the division, must be given by z is equal to 1/2 minus 1/2 I. Here's another example doing a similar sort of thing. This time we're asked to find the number z, which is x plus yi, if when we do the sum on the left hand side, which is z plus 3i multiplied by the conjugate of z, we get the answer negative 1 plus 13i. Well, writing down that equation and remembering that the conjugate z of z is z star must be equal to x minus y times I, then if we substitute for z and z star into the left hand side, then we get the following: x plus yi is z, and then we've got 3i multiplied by x minus yi. Now we can simplify the left hand side, so if we multiply out the bracket, we'll get 3i times x, or 3xi, and then minus 3yi squared. So the I squared again being minus 1, this gives us plus 3y, so that's then a real part. So we've got x plus 3y, and then the imaginary 3x plus y for the imaginary part. So again, once we've done that, we can now equate the real parts and the imaginary parts on each side of the equation. So the real part, x plus 3y is equal to negative 1, and the imaginary part, 3x plus y is equal to 13. Well, we need to solve these equations simultaneously again, so taking the first one and multiplying by 3 gives 3x plus 9y is equal to negative 3, and then the second equation, 3x plus y equals 13. So this time, if we subtract these, we're going to get 8y is equal to negative 16, and so we therefore get y is negative 2, and then by substitution x is equal to 5. And so therefore the value of z must be equal to 5 minus 2i. Well, that's the end of this video. In the next one, which is complex numbers 1.6, we'll be looking at the complex roots and how they link to the quadratic equations.